Hello, I'm here to introduce a conversation between the three of us that you see before you, Rob Tibshirani and Brad Efron and myself. This is really to especially attach to interests of Brad's, but let me introduce myself first. I'm Carl Morris. I'm currently at Harvard University in Faculty of Statistics, and a little bit about my background, and I'll ask the others to do the same after that. I met Brad Efron in 1956 when I was a freshman at Caltech. And Brad's been a great friend ever since, and a research colleague too. Caltech was an interesting place then. Sputnik went off, occurred in 1967. Caltech was very deeply into science, but on the other hand, did very little with statistics and probability, and despite that, many very well-known statisticians were there at the same time, like Larry Brown and Peter Bickel and Mike Perlman and Gary Lorden and maybe others. Brad and I were actually in the same house at Caltech, Ricketts House, where Brad was our social chairman in one year and our senior year the House president. But I decided I was not a statistician's undergraduate. I was interested in math for a little while, was elsewhere, and realized I wanted to do statistics because that connect mathematics with so many other areas. So I went to Stanford, and guess who was there again? Brad was already a graduate student at Stanford. And as were a number of other wonderful people there that have really made a big difference, I think, just to have such great classmates like Joe Eaton and Grace Waba and Mike Perlman again, and Miles Hollander and Paul Holland and others. But also Stanford and Berkeley were together, and we had not only the advantage of Neyman and all that galaxy of stars, but other graduate students at the time like Steve Stigler and John Rolfe and Bruce Hoadley became friends and many others who I'm sorry we can't mention them all. At Stanford I studied under Stein and never did anything with Empirical Bayes, even though that's what Brad and I wound up doing together for a long time. Not too long after I left Stanford, I went to Rand Corporation for over a decade and discovered the power of interdisciplinary research and the wonders of statistics in that way. And Brad, of course, as it turned out, became a consultant to Rand, where he's been active ever since. In fact, it had probably been there before I was. So we've had a long career together, and especially when I was at Rand, we wrote something like 10 papers together, mostly on Empirical Bayes and topics that sometimes now have other terms like multi-level or hierarchical modeling. One of our three in the discussion is Rob Tibshirani, who is currently professor of statistics and another of Brad's long-term collaborators. And I just wondered, Rob, if you'd say something about your career and possibly how it got started with Brad.
Yeah, well, I'm a Canadian. I was at the University of Waterloo, like many Canadians came through Waterloo in the math program, then did a master's in statistics at Toronto. And my mentor at the time, David Andrews, said, well, I'd love to have you stay as a PhD student, but you really should go to Stanford, because that's the place to go. So I did a PhD at Stanford from 1981 to 84. I had a wonderful colleagues, students, including Trevor Hastie, Mike Stein, Art Owen, many of whom have either returned to Stanford or have very, very visible careers in statistics. And Brad was my supervisor until 1984. I then returned to Toronto, where I was a professor until 1998. Brad and I remained collaborators and friends, and our main collaboration was our book about the bootstrap in 1993. Then I returned to Stanford in 1998 and have been a professor there and continued to work with Brad since then.
Well, thanks, Rob, and of course we especially want to introduce Brad, who is currently a chaired professor at Stanford. He, a long time ago, won a MacArthur Prize, the Genius Prize. He's a member of both the National American Academy of Sciences. And I think it's important, he's done many things that I won't mention, but one thing I think is important for some of the discussion that might come up is he's also been a senior member in different ways in the Stanford administration, including tours with the deanship and the faculty senate and some other areas. And Brad, I was just wondering, I'll let you introduce yourself and feel free to open this up more. Would you just say a little bit more about yourself in your early years, whether you decide to start in St. Paul or Pasadena or wherever?
Okay. Well, thanks. Let me first say that the two people up here with me are my closest colleagues that I've had in a very long career, and it's not an accident that they're here with me, and I feel very fortunate. I don't know, where should I start? How about way back at the beginning? St. Paul, Minnesota, my dad was a salesman and truck driver, but he had a great love of mathematics, and he was also the bowling and baseball statistician. And that had much more effect on me than I ever thought it would, because I went to Caltech, where there were wonderfully smart people and almost no statistics. We had one statistics course out of Cy Derman's little book, and then I asked one of my professors, Morgan Ward, if there was anything else I could study, and he gave me Kremer's book, which I read from beginning to end. And I thought this was fitting. Kremer wrote that book in isolation during World War II, and I read it in isolation at Caltech. And I wanted to go into statistics, I decided. I was a bad 21st century or 20th century mathematician. I would have been okay in the 19th century, but I had no mind for the kind of abstractions that dominate modern mathematics. And so I wanted to go into statistics, and I finally wound up, I talked to Berkeley and had a very nice interview with two guys named Jersey and Eric, who I hadn't met before, and they were both very nice to me. Somehow I wound up at Stanford. And when I got there, I found out I was in the math department because my advisors had told Stanford that I was really probably intended to be a mathematician, just a little momentarily confused. So I spent my first year in the math department and then went over to statistics, and that's when Carl and I reunited. And we'll get on. We'll get lots of this stuff. All I can say is that I've had, nobody in science works by themselves, and I've had more than my share of wonderful colleagues. And you just can't do fields like statistics by yourself. You have to have the kind of stimulation that you get from having smart people around you challenging you. And one of the great advantages of the Stanford department has been that it's always been full of people who are quite willing to challenge you in a rather pleasant way.
Now, talking about your years as a graduate student to show that you're very human, is it true that you were kicked out of Stanford as a student?
Yes, this was my subhuman phase, I believe. My first year there, while I was still in the math department, I was one of the reasons I came to Stanford instead of Berkeley is I liked Stanford's humor magazine. I wrote a humor column at Caltech. You might have forgotten my column. Many people have, but and I always wanted to write for a humor magazine. And Stanford had a great humor magazine, the Chaparral, and I went up, and the first few months I was there, the editor went literally crazy and had to be hospitalized, and so I became the editor. And then they, for an issue that it was a parody of Playboy, and it went a little too far, and I was expelled summarily from school, and I would have been expelled forever, except that people like Al Bowker and Halsey Royden, who were high in the administration, said I was a good student. So I went away for 6 months, and then I came back. That was by far the most famous I've ever been, because my picture was on the paper every day, because I fought the expulsion. In those days, I used to kick out lots of people, and I fought like crazy. And in subsequent years, everybody fought like crazy, and they would have given anything to have me back again, because I was much nicer about it.
So I remember, Brad, that you were one of the really good writers, an undergraduate, and also in those days that was part of the reason you were at the Chaparral. What you did right then was just really kind of moderate, so modest now that nobody would think anything. It apparently bothered the local clergy or something. And
I was denounced from the pulpit of the Catholic Church.
Excommunicated?
Yeah, well, they couldn't do that, but they would have if they could have.
But you've used those writing talents. I think it's been part of your success in statistics, not only your wonderful ideas, but your ability to put them in ways that help people understand better. So,
You want to say a little more about your family? I know you have 3 brothers who, some are in academia, and a son who's going into academia.
Yes, my father gave us this pretty clear picture that we weren't suited for heavy work, and so my older brother Arthur is a retired professor of English and a noted expert on romantic literature. He publishes his own journal called Paunch on romantic literature, and it's after Sancho Panza, and I get Paunch, and it alternates between very esoteric English theory and smut. And my 2 younger brothers, who are twins, always were very close. One of them got drafted and went to Don and went to Canada, where he's been a successful citizen, and he runs they're both psychiatric social workers. And Don runs his own journal of family therapy, and Ron has become an expert on unpleasant emotions, and he's written a book entitled, a good relative bestseller called "Angry All the Time," and I leave copies around. My son Miles is one of those stories that you're supposed to hear of a humanities student who suddenly got interested in statistics in the last few years and is now at Chapel Hill working on information retrieval, and calls me and asks me difficult questions about the singular value decomposition, which I cannot answer.
well, you won't be asked here. You know, I remember back in 1960s, a lot of things were happening at once. One was I just couldn't make a career choice, and statistics was a way to do mathematics and do everything in sight. And I think a lot of our students even today say that's one of the great attractions to this field. But it's not only an attraction to it, it's actually a necessity. And another thing that was happening in the 1960s was about then that most of the departments were being formed, you know, plus or minus maybe 5 years. It was suddenly a subject that was just coming on like gangbusters. Statistics then, though, at least when we were studying, was pretty abstract. At least you were by biostatistics partly, but you took all those courses too that were pretty much just pure mathematics. And so I wound up going to Rand to find out something. I thought 1 year, I'll go to Rand for 1 year and learn all about applied statistics. And it took more than a year. In fact, I wound up staying for 11 years, had the time of my life. But I found out that statistics, I know you've talked, Brad, at other times about applications and mathematics and computation and the sort of a triangle of ideas for statistics and how these all tie up. But I also think it's very central to our field, that we keep strong interest in all 3 areas, not necessarily every individual.
It looks to me like your work is getting more and more applied, that you're more and more motivated by real problems. Is that fair to say?
Well, another way to say it is I used to have ideas, and somehow that quit happening about 20 years ago, and now all I have is my colleagues or applied work. We have a wonderful opportunity in statistics. Both men and women, we're the last gentleman scientists in that we can look in on lots of fields and really talk to very brilliant people who are totally confused, and that's the scientists, and then we're supposed to unconfuse them, and it's a wonderful way for me to get into a topic. It's not, but some people honorably want to do the applications for the application's sake, and I always am interested in it for the statistics' sake. So we've been working on microarrays together, for example, and that's been wonderfully stimulating. But I'm not really interested in the biology of microarrays. Of course, I'm interested as an amateur, but what I'm really interested in is how the inference will come out, the inference theory will come out.
One of the things that I found surprising is that how we tend to find statistics relatively easy, but other scientists find it hard. I mean, I have a very good biologist colleague who says it'd be a lot harder for me to teach him statistics than for him to teach me biology. Although when I look at biology, it looks very daunting. It's a huge mass of facts that look mysterious. But statistics is a way of thinking that's very hard for other people to develop if they haven't been trained early on in the field. So it's good news for us that we have something that's quite unique, I think, for
Do
other
you think
scientists.
it's hard, or have we made it hard? And I mean, not you and me, I mean, has the profession made it hard with all its jargon and difficult ways of looking at things?
There's some truth to that, but I think even the important simple concepts aren't as simple as they appear.
Like
I don't know
one?
if you agree.
What's a simple concept?
Well, the idea of doing, say, a permutation test to infer from a set of data a p-value. That's
I thought you might say p-value right off the
Yeah,
bat.
yeah.
See, I think p-values are hard. I mean, they're easy to know as p-values, as we do, because it seems like they arise naturally. But they're very confusing in the sense that people misapply them. They think it's p-value is a statement, of course, about the data given the null hypothesis, and people think it's got something to say about the null hypothesis given the data. And that daunts, Herman Chernoff used to tell this wonderful story about Nobel Prize winners trying to, a Blue Ribbon Committee trying to look at the Kennedy assassination. And these Nobel Prize winners were all befuddled. Something had been significant at the 05 level, and they thought that that meant that there was a 95% chance that there was a second gunman on the grassy knoll. And Herman knew they couldn't have thought that, because that would mean a prior distribution had to be somewhere if it's a posterior, so it must have been a p-value, and he explained it to them. But Nobel Prize winners can't get onto this subject. But it's sort of because the probability of A given B and B given A are two different things that everyone confuses.
Well, another example is confounding, which for us, I mean, a lot of very good scientists design bad experiments that are in which the important effects are confounded with experimental biases. But confounding is something that's fundamental to our subject, and we understand it and know how to adjust for it.
Yeah, I think that many of my scientific colleagues are pretty good at probability. They naturally can do probability calculations and do elaborate models, but they're very bad at reasoning backwards from data to what probability model might have been, and that's statistics. And I remember going into statistics that first year, I thought, well, this will be pretty easy. I've dealt with math, and that's supposed to be hard. And statistics was much harder for me at the beginning than any other field. And it took years before I felt really comfortable, and years of, it's hard to figure out why people do what we do, why p-values, why stuff like that. And you have to do some applications and get some feeling for it. So statistics is the only place that statistical inference is done, and we really perform a service there. It's backwards thinking, right? You think from the specific case back to the general case rather than vice versa. And that, according to the philosophers, that may even be impossible, but we do it every day.
So the specific meaning, I've seen the specific data, now what model, larger idea produced it,
Now, I arrived in Stanford in 1981, a couple of years after you invented the bootstrap. Too bad I wish I wasn't so late. So tell us a bit about the thoughts that led up to the development of the bootstrap and how it happened.
Well, the bootstrap illustrates the value of having good colleagues. Rupert Miller had written a paper called A Trustworthy Jackknife, and which was a very good attempt to give some, when the jackknife came out, Tukey just sort of presented it as sort of a magic thing. And it seemed like magic because you did some numerical calculation, you seemed to get an interesting answer, but nobody could figure out when it worked or when it didn't work. And Rupert started out on that line. And then Rupert and I were both on sabbatical the same year at Imperial College in 1972 with David Cox. And Rupert gave a talk on the jackknife. And David came up to me afterwards and said in his inimitable way, do you really think there's anything to this? And what I realized many years later was he was giving me a strong hint to work on this, and which I did. I was asked to give the Reitz lecture in '79, and I started working on and I wrote down one line of stuff, and it said, what is the jackknife an approximation to? And as soon as I wrote that line, I essentially had the answer. And I started out with something really quite elaborate called, I called it the combination distribution, because I was taking combinations instead of permutations. And then I started to realize I could get rid of some of the machinery. And then I got rid of more of the machinery. Pretty soon there was no machinery. And I thought, well, this is pretty dull. And I gave the talk and everybody loved it. and I've never thought since then that I was a good judge of what I was working on myself.
Now, it was submitted to the annals. What kind of reception did it get at the annals?
I should say that. Rupert Miller was the editor of the annals at that time. I submitted this paper, which was the Reed's lecture, and it got turned down. And the associate editor, who will remain nameless, I hope.
But let's hope he's watching this.
Yeah, he isn't. Said that it didn't have any theorems in it. And so I put some theorems in at the end, and I put a lot of pressure on Rupert, who was next door to me, and he finally published it. And later I was editor of, actually it was earlier, I was editor of JASA, and I did remember a rule that I had was that when papers made people angry, you ought to look at them more closely, because they divided into a bimodal class. Those were the worst papers you ever saw. That was a big class, and a few that were good ones. And since then, I've had many papers that, if you think that every paper I submit gets accepted right away, you're wrong. I've had many papers turned down. I usually work really hard on them. You and I just had one. I really try hard to rewrite. I take referees seriously, but I'm never discouraged by referees not liking something, because often it's because you have some new idea.
One thing I found curious about the bootstrap, I started giving talks about it after I graduated. It was much harder to convince people within our field that it was useful. When I give a talk to physicists or chemists, they go, "Oh yeah, that's simulation. Yeah, we do that all the time." But statistically, as a statistical inference tool, it was really hard for statisticians to embrace it, because it involved, a random number generation, which didn't seem, it's unsettling.
Well, I remember, another thing that's very timely right then is I remember we paid about $300 an hour to use a computer, and 300 was probably more like 1,000 an hour now, and computers were slow. And to do one of these calculations could take minutes to an hour or something. So that was a real drawback. But of course, that just happened to coincide when we were beginning to get our own personal computing. And we all know now it's no big deal, at least at some level. It's still a big deal at other levels. So it was very timely. But this was a rare thing, I think. You said something about 20 years ago. You realized you couldn't think up. You depended on looking at problems or something. That was an example, I think, where you tried to read the literature, deal with something you knew about but didn't know a lot about, the jackknife, try to think up a theory related to it. And the approach of trying to read other people's results and do them one step better, I'm just going to say to students and people trying to do research, I found that much less fruitful than the approach you said you've been using the last 20 years, which is to go get involved in a real problem, and pretty soon you see all sorts of things that have never been worked out. Is that how it works?
I'm a bad reader ab initio, but once I've started working on something, then I want to read everything in that area. And I find it much easier to read once I have a foothold in an area. I can see why people are doing something. That's the hardest thing when you're writing. One of the hardest things to do is to tell people why you're doing something, not what you're doing. And once they understand why you're doing it, there's a good chance they'll be sympathetic, unless they're that particular referee or associate editor. And but I do read, but post more than pre.
So did I wire that properly, though? Did you start more from theoretical ideas as opposed to from a data set trying to solve a problem?
In the bootstrap case?
When you worked on the bootstrap, yes, as you get going on that.
It was more from, it was the fact that a colleague had raised an interesting problem that I couldn't see, that seemed unintuitive to me. And
so it came out of theory.
There's an awful lot of the literature is dull because it's basically surprise-free. You read it, you start at the beginning, you know perfectly well if it's that the answer is going to be. Every once in a while you see something that's surprising. And I remember the Benjamini-Hochberg result on false discovery rates really surprised me. And as soon as I get surprised, then I'll read with a good deal more interest.
Now, another thing that makes you somewhat unique is you don't have very many co-authors. I think Carl and I are some of the very few people that have written maybe more than 1 or 2 papers. You tend to be very, very individualistic in the way you work. Is that...
Well, individualistic is a polite term. Rob may be saying I'm a somewhat difficult co-author. First of all, I don't understand anything, and then when I do understand it, I insist on saying it my way, and my attention span wanders quickly. One of the wonderful things about statistics is you really can look in a lot of different fields, and for a person with a short attention span, it's an ideal field because you can go, if you get tired of doing biopsy data, you can go off to astronomy data, and our field is really not very filled in. If you made a picture of mathematics, there'd be a very dense central spot, big area with little spots going out a little bit from the central area. If you made a picture of statistics, it'd be much more diffuse with many more open spaces between the known areas. And I love that about the field.
So I know one other thing the bootstrap did, which was give many statisticians, especially frequent statisticians, an excuse to have someone buy them a computer. And that changed things, and the Bayesians got left behind for a while. But of course later the Bayesians came up with MC and with the Gelfand-Smith paper and other things, and suddenly everybody in statistics had a computer. And as I turn to that, Empirical Bayes, which is another topic I think you've dabbled in, quite a few times actually, both with and without me. Brad and I probably did about 10 papers, but there were others. And I kind of want to get an idea. I know you talk about Empirical Bayes sometimes, and you think it's an underachiever, you said in one of your talks. Why do you say that, given all the other things connected with Empirical Bayes that are widely pursued?
Yeah, when I said that Empirical Bayes was an underachiever, I meant in comparison with things like Wilcoxon's test, which are used billions of times. People do use Empirical Bayes ideas, or hierarchical Bayes ones more generally, but it really hasn't spread into the applications community. And also I was thinking in terms of the possible gains. The things like Wilcoxon's test really aren't much of a gain over a t-test in experienced hands, but Empirical Bayes can surprise even statisticians with how much you can gain, or Bayes in general, but Empirical Bayes in particular, because of its applicability. You can easily save 75% or 50% of the risk. So why isn't it used more? And I think the reason it hasn't been used more is that we're not too confident about the theory of when it applies, and it hasn't spread there's millions of analysis of variance is incredibly useful. It fits so many situations. Well, part of the reason it fits so many situations is that Fisher taught people that we can handle analysis of variance very well. So researchers design experiments with us in mind. And if we get good at analyzing Empirical Bayes situations and confident about it too, both in a theoretical and applied sense, then I think experimenters will start designing experiments that make use of the kind of parallel nature you need for Empirical Bayes, microarrays being a good example.
Well, I think another important thing is that people tend to use tools that give them answers where they didn't have any answer before. Whereas, like robust statistics, for example, was very big in the 60s, but how many people use it now? I mean, the thing is, it gives a perhaps higher quality answer to a situation we already had an answer. The bootstrap, on the other hand, gives an answer where we had no answer before. And that's the kind of tool people are really going to use, where they can analysis of variance as well. It's a basic tool that gives us an answer to questions which are important scientifically.
There's one other thing, and that is the bootstrap's easy to use, and methods that get used a lot are easy to use. And
of course, easy doesn't mean it means, in the sense, the computer has to work like that,
right.
but it's easy for the person who has to program the computer.
The kind of thing that's hard to use is a theory like uniform minimum variance unbiased, where you have to think for each new case of a new trick to apply it. The things that go like gangbusters are things like maximum likelihood estimation, where one algorithm fits all. And so when you get going along those lines, and maybe what we're saying is that Empirical Bayes needs to be algorithmatized more.
Well, One way I look at what you say is empirical Bayes and can be thought of as part of a random effects or two-level model is it explains regression toward the mean. And to me, regression toward the mean is a bias. Anything's a bias if I know in advance what's going to happen. Of course, you know, I've used baseball examples. So the team that wins the pennant most years, about 80% of the time next year they'll have a lower won-loss percentage. And that's because they were up at the top for two reasons. They were good and they were lucky, and the luck part needs to be knocked out. And Empirical Bayes does that. I think you've also suggested sometimes that it's biased to use, you've said we need to get away from the notion of unbiasedness so much. To me, correcting for regression to the mean is being unbiased, and not correcting for it is a bias. Rob, you know, you can answer these things too, because these are general ideas in statistics. But I think that this tool of hierarchical modeling or empirical Bayes is it's widespread. I mean, lots of people know recognize regression toward the mean and what small samples can do to produce large.
But I think the point is, Brad's making, it has to become semi-automatic before it's really going to become widespread. If it takes a PhD in statistics to apply it every time, there just aren't enough of us around to make it a widespread tool.
So lots of different packages now have methods, for better or for worse, I might add, not always for better, of doing this stuff, shrinkage and so on. Is that hasn't gone far enough in your mind?
Well, I don't have that much personal experience with them, but
yeah.
When you use a Bayes or empirical Bayes estimate, you don't have the safety of each theta is estimated unbiasedly by its x. And that's what you get from the Fisher kinds of theories, is maximum likelihood estimation. Essentially, each parameter you know is going to be pretty well estimated from its own data in a way that is fairly unbiased. If you use an empirical Bayes estimate, everything gets pulled toward the central bulge and you have to grit your teeth and take the fact that even though any one estimate may not be improved, overall you're getting quite a bit of improvement. That's what we have to get people, including ourselves, to believe, and you have that's hard.
Right.
It's hard for me still.
I actually believe they're all improved, and not in the sense of Stein, but in the sense that on the basis of the information I have available to me, every single one of them is more likely to be an improvement than not. Now later, of course, if you tell me the true values, I'll find some were better than others. But
you may know, for example, that some of them are likely to be underestimated almost surely by 80% chance or something, that they'll be less, the point estimate will be less than the true value. If one that's out on the far end and is pulled in.
Yeah. No, I don't think
You
that at all.
don't believe that?
No.
You've been sold on this stuff.
No, I've proved it. I mean, I've convinced myself, let's put it down. I don't think anybody sells stuff exactly, but no, I think, you know, if you have both levels of the model right, then basically you're targeted after you pull things in. And it's, the trick, of course, maybe your point you're making is it's hard to know about the second level of the model, which is some kind of exchangeability of the parameters or maybe something more complicated.
Yeah, so as we've written, you have to believe that all the parameters, you're testing penicillin and ampicillin and 10 other kinds of antibiotics, and you've got an estimate for each one, and you have to believe that all the data has some implications for penicillin, not just the penicillin data.
Yeah, now you have to decide whether you're willing to combine that. The data is supposed to help you decide whether you can do that shrinkage. I remember Robbins once complaining about
Yes, I do.
these types of things where you bring up different things. But I look at a lot at hospitals, and I tend to shrink VA hospitals who are doing certain kinds of procedures together. There are 160 of them. And I believe the information that's in one has some relevance to the other, and I don't know how much, but the data help me.
Yeah, but if you went to the hospital with the best score and told them that you were shrinking their score down because you're pretty sure that a good part of it was luck, they might not agree with you.
They wouldn't like it, but I'd be right more often than not.
Yes.
They wouldn't like it.
It's a lonely life being
It's
right.
a lonely. And I think maybe that's why we still have a long way to go. It's also very hard to teach these ideas in a first course, and many of the users out there haven't had much more than a first course.
Well, I think the serious point is that 20th century statistics mainly taught us to treat each parameter in its own right and try and essentially estimate it unbiasedly or test it with an unbiased estimate. And that's what I meant by modern technology has to, you have to accept that you're not going to be able to have that safeguard.
Well, you also made a good point maybe before that I think science asks us the kind of questions that we teach them to ask. For example, they ask us about t-tests because that's what they think we can do.
Yeah.
But, right? And that's, sometimes I think that they think that's all we can do, unfortunately. But as they learn more and more about statistical science, if we can do, for example, treat parallel problems well with empirical Bayes, then we'll get asked that question more
So
often.
we might try teaching our beginning courses in a little different way. For example, if we teach people who will never be statisticians,
Right.
But maybe they can be MDs someday or lawyers or something, we ought to teach them what statistics can do,
Right.
what kinds of problems come up, and pretty much tell them to hire a statistician. That could, and they might like our courses more too, because maybe they'll see how our courses have something to do with what they need to know and not just some kind of torture
Right.
semester.
Well, right now we teach pretty much historically. That is, we start out at the beginning of the 20th century, essentially, with normal theory methods and work up to more complicated parametric methods. And then maybe in the third quarter or something you get non-parametrics, whereby if the field had progressed in the other direction, if computers had been available before math was available, we probably would start with non-parametrics, which are basically simpler and easier to explain, and then we'd get to that terribly tough stuff, the t-test and the normal theory near the end.
So in a sense, we teach drivers, somebody wants to learn to drive a car, and we teach them at the beginning how the engine works.
Of the Model T as well.
And a Model T engine works, and where they just want to drive. But we have certainly different audiences.
Now, we've talked a lot about Fisher, and I know he's one of your intellectual heroes. Who else in the last 50 years really has had a great influence on you?
Yeah, well, Fisher should be everybody's hero because we were incredibly lucky to get a mentality of that level in our field. It's hard to say heroes. There's some people in this field that I've admired extremely much for both their mind and their work. Neyman, Rupert Miller. If I look at my work and say, who's influenced my work, if I judge heroism that way, Charles Stein, who I also admire very much, Herb Robbins, Rao, and younger people too, including the two people on this stage have...
Younger? Thank you, Brad.
Carl is 3 months younger than me, and he always makes a point in that 3-month interim to make a point that he's a year younger.
How about David Cox?
Very much so, and without any close personal contact or anything like that, as an exemplar of clear thinking about inference. I don't think you can do much better than Cox, who brings the Fisher tradition still. The Fisher tradition, it's hard to see how it's doing these days. There isn't another Cox in sight of that level, and I hope it's not fading, because that's a wonderful tradition that's very well attuned to the needs of the data, the community that does statistical inference.
Now, what we need to have another Cox. I mean, that's an amazing statement. I haven't heard you say that we don't have another David Cox coming.
Well, I'm not sure of that. It's hard. I'm too close to the time to say that for sure. But I don't see the Fisherian heritage comes mainly out of England, and where and it's just a wonderful way of looking at statistics that really isn't either Fisherian or either frequentist or Bayesian, and it's got a lot of spirit of compromise and give in it, and also a lot of algorithmic wiseness, and I don't see that wisdom alive very much in England anymore. I'm no expert.
Well, we hired them all away to the United States.
And then the United States has not been as friendly a ground for Fisherian thinking. frequentist thinking and what may be considered even beyond frequentist thinking, the kind of atheistic thinking that goes into these prediction models where they don't actually believe in any form. People forget that Tukey and Mosteller wrote a book together, the Green Book, the famous Green Book. If you look at that book, you'll see that there's no probability in it even, let alone any theory of inference. And they really, you can go beyond frequentism to almost atheism from a statistical point of view. And the United States has not been fertile ground for the frequentist, for the Fisherian point of view. I hope that it comes back, because it's a very valuable part.
Be changing. It seems to me that Fisher couldn't have been Fisher if he had been as brilliant as he is, and even hardworking, but had not also been involved in real problems. He was a great geneticist, but he also worked in agriculture and developed experimental design for that. In other words, he was someone with immense theoretical talents who worked on important applied problems. And I think there are people doing that, and if they have I'm worried more about the loss of the theoretical side. Maybe there's...
Well, I worry about the loss of models. Like what Tukey did in the 60s was really say we don't need models anymore. I mean, I think he swung the pendulum too far with his exploratory data analysis, and now there's similar things happening in machine learning where we're saying, well, all we need is these fast algorithms that are accurate. We don't need a model. But one of the themes of my work recently is to try to bring us back to models to say, well, if you have an algorithm, to understand how it works, you need to know what model it's fitting. And I think that's still a very fertile idea. And I think the core of our field really is modeling.
Sometimes
understanding models.
Sometimes I think the reason we do something is get an estimate.
Right.
And one way I tend to do it is get a model and then get an estimate of the model. But I think the deeper science is the model itself. That's what empowers somebody, even if my estimate is boring a year later. Right. Someone else might be able to use that model and carry it further.
Models, the concept of models are very closely tied up with the concept of optimality. You can't really talk about optimality till you have a model. And what the machine learning people are not very interested in optimality right now, but there's really no science, in the long run, there's no science there unless you start bringing it back to a theory of the best you can do.
Right.
So I hope that models come back too. But, you know, they're easy to criticize because people overdo them.
Right.
I think that's terribly important. And Rob, I hear you defending models where I think you probably are more non-parametric than I am, and yet you're regretting the loss of models, or... Well,
but I mean, the models can be more and more adventurous. They don't have to be simple linear models, but you should always have a model in mind so you know the situation where you're doing the best you can. Because to know when a method fails, you have to know, first of all, where is the ideal method, and then you can move from there and say, well, here's a case where it won't work. And to understand operating characteristics, you have to I think you need models.
I think a model is an oversimplification sometimes, but hopefully not too much of one. Yeah. It's a great simplification of a complicated
probability
reality.
Is a tremendous simplification, right?
Things
are happening, a lot of things are happening that are sort of unexplained and noisy and stuff like that. And the idea of probability simplifies that greatly, and then a model for the probabilities simplifies it further.
Yes. Yeah.
So we're trying to get into our little brains' complicated world, and then let alone be able to manipulate it and predict it is a tremendous achievement, and you need help. I mean, the fact that you have a big computer and you can do any calculation you want.
How do you know what calculation you want?
Yeah. I gave a talk to the American Math Association once, and first thing I noticed was everybody was incredibly old. That's when I wasn't incredibly old.
Right.
I started out by saying that what would happen in mathematics if somebody invented a infinitely fast computer. So you could bring it home and take it out of the box, and by noon you could settle the zeta conjecture and the Goldbach's conjecture and all those things. And I said, would this be the end of mathematics? And then they were looking really worried by this time. And so I said, well, no, it wouldn't be the end of mathematics. People would just start interpreting the machines differently. And I said, something like this has happened in statistics. We can answer the old questions that were so hard, almost any of them. We don't have to have a distribution that's particularly tractable or anything like that. We can answer all our old questions rather easily. Now, does that mean the field is through? No, we've just started asking many more questions. There's more statisticians now, and it would be good for mathematicians too. They didn't believe it for a minute.
And now, speaking of getting incredibly old, a lot of statisticians, when they hit 60 or 65, they start to do philosophy. They sort of find that the grand unified theory of everything. But you haven't done that. You seem to still work on applied, smaller problems, the real applied problems. Has that been a conscious decision? Or?
Well, I usually don't think about such things, but when I was 60, that is a morbid date in which you start thinking about things, and I started thinking, now maybe I shouldn't. My plan so far has been no plan. I just work on whatever is fun that comes along, and whatever colleague seems interesting or whatever paper seems interesting. Maybe I really ought to concentrate on trying to do one big thing, and I thought about that, and I found, first of all, I couldn't possibly follow that advice. There's no way you can sit down to do one big thing, or at least I can't. So I just went back to doing lots of little things, and hope that one of them will turn out okay. Statistics is a wonderfully forgiving field. You don't have to be the brightest person in the world or work day and night. All you have to do is get an idea and keep at it. Most of the time, like I said, most of the field is not filled. And so I like working on little problems.
One of the challenges I found is that we're a funny field in the sense that a lot of other people who aren't statisticians do statistics, whereas we don't do chemistry or biology. We don't go into a lab and start filling up test tubes. Yet statistics is something you can do if you have a PC, right? That's all you need is Excel and a PC. So it's a challenge in the sense that a lot of people think they can do it well, but aren't doing it well. So we have to not only do good statistics, but sort of spread the word to other sciences about the right way to do things.
Yeah, so statistics is fundamentally, if it's going to survive, interdisciplinary, and I want to make sure we save some time to talk about another topic that I think, actually both of you guys, but certainly Brad, too, has a real perspective on. I emphasize, Brad, that you have had some administrative positions at Stanford that have let you take a bigger view of the role of statistics and how Stanford has been just marvelous at. You have a very strong department that's been very strong in your university with interdisciplinary appointments. And I think a couple of questions I'd like to ask, put up for us to discuss. One was, why should we try to preserve stat departments? I'm sure statistics will survive. We'll statisticians in stat departments. Why should we keep stat departments? And what can we do to keep them strong and the field strong?
I was associate dean for a while, which is described by one of my colleagues as a mouse training to become a rat. And I was associate dean for science, and it was really quite an interesting experience. It's not easy doing these things. Statisticians have quite an advantage in the dean's office because we deal with lots of different fields, and no other field deals with lots of different fields. They only deal with their own field. Statisticians are also good at comparing things, which is what you do a lot. when you can't say whether A or B is good, you can say whether A is better than B. And I spent a lot of time talking to other scientists, and they're wonderful. But I wound up feeling that statistics was a very fortunate field, and that we weren't. First of all, we're sort of small and not overhyped in the press. We're not under tremendous pressure to raise money. Biologists and chemists are under tremendous pressure to raise money to keep big labs going, because that's the only way you can do the science. You can buy a computer for pretty cheap these days, and you don't even need one if you don't want to work that way. Statisticians are nice to each other. Some fields are horribly competitive, and because statistics doesn't have huge prizes or a lot of publicity, people are pretty much good to each other, and we tend to argue a lot, but basically we like each other, and we praise each other's work in our hearts, at least, if not necessarily in the pages of the journals. I came back to statistics very happy and hoping that our little department would continue to do well. As we said before, statistics departments are the only place in the world where inference is generated, that in industry and places like that where they have serious statistical enterprises. And so if statistics departments stop, people will be able to keep doing the stuff we have, but there won't be any new inferential ideas until another Fisher comes along. You said Fisher wasn't a statistician. It was almost impossible to be a statistician until Fisher. Mm-hmm. And he really, well, other people too.
So are you optimistic about our field?
Yeah, I'm not one of these cheerfully optimistic people about everything.
I know.
Yeah. I tend to see dark clouds before I see silver linings. But it seems to me if you look at statistics over the 20th century, it's almost a steadily rising curve. And it's easy to underestimate how much effect we've had. But no other field has taken over dozens of other fields as the main way of doing science. And we have. We've just replaced the case history method in medicine with the comparative experiment. And medicine moves much faster now.
I think the thing is, we've done it very quietly. It's one of the reasons why people haven't noticed, right?
Well, yes, and we've
slow
also
change.
handled it differently than math. Math used to say, oh, well, this applies to some field like physics. That person's really a physicist. And they keep the subject pure. I hope we continue to value all these different connections and to value the people who can make those connections.
One thing I've been thinking might happen, just from experience around Stanford, we accept right now there's biostatistics departments as well as statistics departments. There might be astrostatistics departments or geostatistics departments springing up because those fields are starting to use statistics much more. As in physics, they used to have, 10 to the 26 particles for any experiment. You don't need statistics. But when you get down to situations where you're looking at maybe 10 or 100 newly generated particles, suddenly inferential efficiency becomes all important. So we've had talks from the physicists in our department now about statistics and vice versa.
And another example is DNA microarrays, right? A lot of genetic areas, you don't need a statistician to tell you that there's a huge effect. But now when you're looking for 6,000 possible effects, you need a statistician to help sort the signal from the noise.
Absolutely.
So we're getting near the end, and I hope each of you will add some brief comment. But what I think to summarize a couple points there is, I think the world would really be set back if we didn't have statistics departments, because the stat department is the way that we reach out and communicate and have interdisciplinary connections with many other fields. It's also been a lot of the fun of the subject, and I think we'll get people who love to do that, and not everybody has to do it all. But a stat department can facilitate the infusion of good statistical methods into many fields if they'll do it. Now, they have to take that seriously, and they have to get staff, faculty, and trained students who want to do that. If we isolate ourselves and start trying to show off for each other, not for anybody else, we'll ruin that. I also think that applied problems are a great source of new theories. And I think that's what Brad was saying, that they stimulate theory. So I didn't mean to stop everything there, but I wanted to make sure we wound up.
Well, I agree completely. I mean, for statistics to flourish as a science, we have to have departments to help cultivate that. If we're just a series of tools that are used in various other sciences, we won't flourish.
And we have to be able to convince provosts and deans and so on that they should put aside precious monies in order to do that, to keep departments alive.
Well, in academia and in industry and government, but especially in academia, ideas are the coin of the realm. And what we really have to do is keep coming up with good ideas. And the field is, I looked at the field thinking about sitting here, and we have produced good ideas, not hundreds of them, but every few years there's a good new idea that comes out of statistics. And if we can keep that up, there won't be any worry about the future of statistics departments.
And a good idea is, of course, something that reaches not just into one subject, but into many, and it's a fundamental idea of some sort. So, well, Brad, I think I've always looked to you for leadership here. as I do too, though, a great faith in the future of this field, and I respect you as a scientist as well as a statistician, and I think you've collaborated with many scientists, and I think, I know you see statistics as important to many sciences, and really it's getting stronger, and I'm really just love hearing those words, because sometimes you struggle, and you find a dean or somebody's being a little hard. Although lately I think that Harvard things have been great. We've hired lots of new people, and hopefully that's the way it's going to be.
Every field thinks that the dean is after them, and most of them are right.
So I've got to, we need to summarize now, and I'll just say thanks to a few people. First of all, thanks to the University of Connecticut and to Harry Poston in particular for setting this up the 17th, as part of the 17th Pfizer Central Research Symposium. I may have used the wrong word, colloquium. And I want to thank Rob Tibshirani and Brad. And also, Brad, I want to thank you for choosing me to be here with you today, because Brad picked his
Yes, same here. Thank you, Brad.
I think I chose very wisely, wouldn't you say?
Thank you.
Good job, Rob.